Golden Iris Productions presents An Introduction to General Relativity and the Schwarzschild Solution by Mark F. Dennis, Exploring Gravity Through Time Gradients. In this section, we explore gravity from a different perspective. Instead of beginning with force, we begin with time. We will see how changes in the rate of time across space can give rise to what we perceive as gravitational acceleration. Overviews. We will begin with Einstein's original problem, then move to Schwarzschild's remarkable solution. From there, we will examine time dilation, the Schwarzschild radius, and how gravity can emerge from time gradients. We will also explore an equivalent interpretation based on vacuum permittivity and show how these ideas remain consistent with general relativity. Einstein's problem. Newton described gravity as an instantaneous force, but special relativity forbids anything from acting faster than the speed of light. This created a conflict. Einstein needed a new way to understand gravity. In 1907, he had what he called his happiest thought. A person in free fall feels no gravity. This idea became the foundation of the equivalence principle. Schwarzschild's breakthrough. In 1915, Einstein published his field equations, but he didn't have a solution for a real field around physical mass. Carl Schwarzschild read his field equations and solved them while serving on the front lines of World War I. His solution described the geometry around a spherical mass. It became the first exact solution to Einstein's equations. The Schwarzschild radius, r sub s equals 2gm divided by c squared. The Schwarzschild radius defines a critical boundary. At this radius, the escape velocity equals the speed of light. If an object is compressed within this radius, it becomes a black hole. For the Sun, this radius is about 3 kilometers. For the Earth's, it is less than 1 centimeter. Gravitational time dilation. Tr over T infinity equals square root of 1 minus Rs over R. Gravity affects time. Clocks closer to a massive object run more slowly. As you approach the Schwarzschild radius, time appears to stop from the perspective of a distant observer. This is not just theoretical. GPS satellites must account for this effect. Without correction, their timing would drift and navigation would fail. Light appears slower in gravity. C of R equals C times square root of 1 minus Rs over R. Locally, the speed of light is always constant, but to a distant observer, light appears to slow down as it climbs out of a gravitational field. This produces gravitational redshift. The effect is not due to light changing its nature, but due to time itself, running at different rates. Gravity from time rate differences. G equals c squared over 2r times 1 minus t squared over t prime squared. Now we connect time directly to gravity. If we compare time at two different locations, we can define a ratio. T squared over t prime squared equals 1 minus r sub s over r. Substituting that ratio into this expression produces the familiar gravitational acceleration. G equals c squared over 2r times r sub s over r. The result is Newton's equation. G equals gm divided by r squared. This shows something profound. Gravity can be derived from differences in the rate of time. Permittivity, interpretation of gravity. The speed of light is c equals 1 divided by the square root of epsilon naught times mu naught. The speed of light depends on vacuum properties. If the apparent speed of light changes, then the vacuum itself must be changing. Epsilon of r equals 1 over c of r squared times mu 0. Now relate to gravity. 1 minus epsilon 0 divided by epsilon of r equals r sub s divided by r. Finally, g equals c squared over 2r times 1 minus epsilon 0 over epsilon of r. This leads to a new interpretation. Permittivity becomes position-dependent. When expressed this way, gravity can be written in terms of vacuum permittivity variation. This form is mathematically equivalent to general relativity. What this means: we now have three perspectives: time dilation, light speed variation, and vacuum permittivity gradients. These are not separate effects. They are different descriptions of the same underlying structure. In general relativity, this is spacetime curvature. In a vacuum-based model, It is variation in electromagnetic properties. Both lead to the same physical predictions. Summary: Schwarzschild provided the first exact solution to Einstein's equations. Gravity creates a smooth gradient in time. Light appears slower because time itself is stretched. Gravitational acceleration can be derived from time differences. It can also be expressed through vacuum permittivity. Together, these ideas form a bridge between gravity and electromagnetism. Thank you for watching. To be continued. Stay curious. If you have questions or thoughts, feel free to share them and stay tuned for the next part, where we go deeper into the structure of spacetime.